Hello and welcome to a supplemental lecture for my class PSYC 440-640, which is called Experimental Methods, but is really a kind of a review and extension of univariate statistics. It's a class that I teach at NDSU. It's the spring of 2016, and I made this supplemental lecture because in Unit 3 of the class we've been talking about ANOVA, mostly one-way ANOVA, what it is, how it is a special case of regression, how to interpret different elements of the output, and how to do cool tricks with ANOVA. And one thing that I think is challenging for students sometimes is understanding the different ways that we can code levels of a predictor variable, or what's sometimes called a factor in ANOVA, so that we can get interesting comparisons between those levels. Now, this is something we often want to do in ANOVA because when we're doing ANOVA, we're often comparing across on some outcome variable across different groups, and we might wonder, is a placebo group different from a low dose group, or a low dose group different from a high dose group? In order to answer those questions, we often need to do comparisons or contrasts, and we can accomplish these by using different sorts of coding schemes. So as an overview for today, what I want to do is talk about some of the different contrast schemes or coding schemes that we could use for ANOVA, kind of briefly consider how they work, and talk about how we can do them in SPSS, specifically if we're treating them as regression, or if we're using the regression module. And as I've already said, and as I'm sure many of you know, ANOVA really is, or at least really can't be thought of as just a special case of regression, a case in which the predictor variables, or again they're sometimes called factors, are categorical in nature. So how do we make the regression module in SPSS do ANOVA for us, and make it do ANOVA in a way that's useful or interpretable with respect to the hypotheses we have? Well, rather than just talk abstractly about this, I want to use an example. This is kind of a fictitious scenario with some fake data that I made up. Let's imagine that you're an educational psychologist who's studying different teaching styles, and particularly you're studying how the feedback that teachers give to students influences how much they tend to pay attention or persist on challenging tasks in class. Many of you of course, are interested in educational psychology. All of you, of course, have had experience of being taught, and some of you experience of teaching, and so you know this kind of makes sense, or it's probably a question that is worth answering. Let's imagine, to answer this question, you conducted an independent you conducted a study that had an independent experimental design, meaning people were, or students I guess in this case, were randomly assigned to different groups that correspond to levels of a predictor variable. These are going to be different levels of feedback, or different types of feedback. So we have 3 groups or 3 levels. In one group, students are given feedback when they failed a particular task that they're working on. They're told, you got that wrong, or you're really doing poorly on this task. Poor kids. In the next group, students are given no feedback as to whether they're doing well or poorly on the tasks that they're working on. And then the third group, happily, those students are given feedback when they're succeeding. You're doing well, or you got that one right, or something like that. So that's the predictor variable. The outcome variable is persistence, and maybe we could operationalize this as how many problems a student attempts before they give up, or before they say they don't want to continue any further. So again, you could imagine students are randomly assigned to 3 different groups. Students within each group are given a set of problems to do, and the outcome variable, or the dependent variable, is how many of them they'll attempt, and the independent variable, the predictor variable, is going to be the type of feedback they get from the instructor depending on which group that they're in. This is of course a pretty simple example. I've made up some fake data. You can see here an image from an SPSS data file that I've set up. We've got 24 students in total, 8 of them randomly assigned, let's imagine, to one of 3 groups. 24 is a pretty small sample size. 8 subjects per group is a pretty small sample size, especially for an independent design. So we probably wouldn't want to do a study that's this small in real life because we'd worry a lot about our statistical power in our hypothesis testing. But maybe it's a pilot study, maybe it's exploratory research, or of course in reality it's just fake data that I made up. Okay, so let's consider how we would approach our analyses with contrast coding. And I'll review in a few more slides what contrast coding is, but before we get there, I think it's important to first consider what are our hypotheses. Now, we could have different sorts of hypotheses for this data, but I'm going to pick a couple here that make sense for illustrating contrast coding. So the first hypothesis might be something like negative feedback is just bad. To be a little bit more clear, we might predict that students in the failure group, students who are told they're doing poorly or getting these problems wrong, will just attempt less of them than students in either of the other two groups. Then we might have another hypothesis that's something like positive feedback is the best. And again, to be a bit more clear, we might say, well, students in the success group will attempt more problems than students in the no feedback group. Now, clearly, the way I'm describing these hypotheses is pretty vague. Again, it's a practice example with fake data. I just wanted to pick a few hypotheses that kind of work for contrast coding, but it's worth considering that when you're doing your analyses for real, there's some value to having specific hypotheses, and I'm not really probably doing as good a job as I could in this example in being specific and clear about my hypotheses. Another thing to note here is that these hypotheses, as vague as they are at least directional in nature. I'm talking about differences that are either positive or negative, doing more problems, doing less problems. Now, assuming I have a fairly strong reason to make those directional predictions, maybe based on a strong theory about the effect of feedback on persistence, or maybe a strong body of literature to refer to, past studies, etc. I might be very comfortable making directional predictions, and I might want to because it'll tend to give me more statistical power to detect effects, i.e. it'll allow me to do one-tailed hypothesis testing, which could be handy later. So anyway, those are my hypotheses. What I want to do is represent those hypotheses with a set of coding variables, because if I'm going to attempt this analysis in the regression module of SPSS, or for that matter using regression in Excel or really any other spreadsheeting or stats program, I need to represent those different levels, failure, no feedback, success, using a set of coding variables. Now there are 3 levels of my predictor variable, or factor. So I know I'm going to need 2 coding variables, and those are right there. They're x sub 1 and x sub 2. And what I'm going to do is code them in the following way. X sub 1 has the value of -2, 1, and 1 as I step up across those different groups. X sub 2 has the values of 0, -1, and 1 as I step up across those groups. This will probably look familiar to you because it's essentially the same coding system that I used in a different example in class, so familiar if you're taking my class. If you're really perceptive, you may notice that these are Helmert contrasts, which are just a common contrast set that are used a lot of times in research, especially research in pharmacology or in treatment studies where there's a presumed dose-effect relationship. There isn't one here, but suffice it to say they're still Helmert contrasts. The essence of Helmert contrasts is you take one level of a predictor variable and compare it to the average of all subsequent levels. So the failure group compared to the average of the no feedback and success group, and then for the second contrast there are only 2 levels left, so it's just the no feedback group compared to the success group. So again, this is the coefficient for this first predictor variable will test our first hypothesis quite nicely. The idea that the failure group will differ from the average of the no feedback and the success group. and the coefficient for the second coding variable will test our second hypotheses. That's of course why I chose them that way. Also, I guess I could have mentioned this earlier. If you're paying attention in class, or if you're familiar with Helmholtz contrasts, you know that these are orthogonal contrasts. And I'll talk a little bit more about that towards the end of this lecture, so in quite a few more slides. So anyway, those are my codes that I've decided, kind of on a scrap of paper, I've sketched them out. Here's what they would look like in my SPSS dataset. I would just take those codes and apply them to each case, each participant, or each student in my dataset. Those in the failure group get the codes -2, 0. Those in the no feedback group get 1, -1, and those in the success group get the codes 1, 1. Now once I've got these codes, I can use the regression module in SPSS to conduct my analysis. So I'm essentially doing an ANOVA within the regression module. Now of course you could do an ANOVA in the ANOVA module of SPSS or in the general linear module of SPSS, but I'm choosing the regression module because it allows me to play around with different coding schemes, and also it's one that I think if you're comfortable working in the regression module, it's a really nice way to go. You can get lots of information you want, you can test comparisons you want. I think it's really useful. So anyway, what I'm doing here is I'm taking my outcome variable, which is number of tasks completed, I'm putting it in the box for dependent variable or outcome variable. Those are synonymous. And I'm taking my two contrast code variables, I'm putting them in as independent or predictor variables. And if you've used SPSS before, you know that you can dial in all sorts of additional options and statistics and regression diagnostics, etc. I'm largely ignoring those right now. Let's imagine I'm just hitting OK and running my analyses. I'll get a whole load of output, including these three tables: the model summary, an ANOVA table, which appears in the regression output, and a table of the regression coefficients. Important thing or interesting thing to notice right away is that the overall model, technically the overall augmented model, is significant. That means that a model which includes coding for level of the predictor variable, level, which group a particular student is in, does a better job at explaining the variance in persistence than does a model, a compact model, that includes no information or no coding about the predictor variable. So, knowing something about whether students are being told that they're failing or told that they're succeeding or whatever else allows you to explain how little or how short or how long they persist. You can see that in terms of the hypothesis test significance level in the ANOVA table. I guess if we want to be a little bit picky, we might say it's just right on the margin of being significant. We can also see that in the sample, membership in a group or a level of the predictor variable explains about 50% of the variance in the outcome variable. That's our I should say explains about 25% of the variance in the outcome variable. That's R squared. Notice, interestingly though, that there is a significant amount of shrinkage. The adjusted R squared is about 17%. So in the sample, we're explaining about 25% of the variance in the outcome variable, but if we were to try and estimate how much variance we would be explaining if we had the whole population of data rather than just a sample of it, our best estimate is closer to 17. Now, why that is so, is due to the fact that our sample size is rather small. That adjusted R squared is computed using a formula called Ware's formula that includes the value for the sample size. And basically, as sample size gets larger, the estimate that you make of the effect size, R squared, gets better. So shrinkage or a discrepancy between R squared and adjusted R squared is usually much more noticeable in samples that are rather small than samples that are rather large. Okay, so let's look at those first two tables. If you go down to the table for the coefficients, you can look at the values for the significance level of my two contrast-coded variables, and you can see that the first contrast is significant, but the second one is not, even if we were going to use one-tailed significance testing, meaning even if we're going to take those significance values and divide them by 2, to make them smaller, we still wouldn't find a significant effect for that second contrast. Even one-tailed testing, that would still be much greater than 0.05. Now, the fact that first contrast is significant and the second one isn't probably wouldn't come as a surprise to you if you'd made a graph like I have here of the level of persistence, the number of tasks completed for each of our groups. And to step back for a second, I would say, as I often say in class, that a good first step to any data analytic approach is usually to try and make some graphs, because they can help inform your thinking, help you kind of consider hypotheses before you sort of launch into running regressions, ANOVAs, etc., etc. So again, looking at this graph, you could kind of imagine that the average of the no feedback and the success group, if you sort of average them with your eye there, would be higher or bigger, more tasks completed than the level of task completion in the failure group. You can actually see this more clearly if you create graphs for the contrasts, and this actually isn't very hard to do. All you need to do is enter those contrast coding variables as the variable on the x-axis when you make the bar graphs in SPSS's chart editor. Note, you might have to change the coding on the variable view from scale, which might be the default, to nominal, so that SPSS treats that -2 and 1 and that -1 and 1 as if they're groups, which they are. But the point is, if you if you just treat them like groups and then compare then graph them, you can see that for the first contrast, where -2 corresponds to the failure group and 1 corresponds to the average of the no feedback and success group, there clearly looks like a significant difference there. Those error bars overlap a little, but neither overlaps the mean for the other group. In comparison, that second graph over there on the right, where -1 corresponds to the no feedback group and 1 corresponds to the success group, those error bars overlap quite a lot, and indeed they overlap the means. Each error bar overlaps the mean of the other group, suggesting that it's probably not significantly different, or almost certainly not. So just looking at the graphs, you could probably guess that the first contrast will be significant, the second one probably will not. So looking at the significance levels, you can consider the tests of your hypotheses. You might also look at the unstandardized regression coefficients and ask yourself, what do those actually mean? What does that number 0.35 mean, or that number 0.31? Well, if you remember from class or from reading the text, you know that to figure out what those regression coefficients mean, all we really need to do is plug in values for the different contrast codes that we have and solve for b sub 0, b sub 1, b sub 2. It involves a little bit of algebra, but once you've done it once or twice, it's really not all that hard. So let's consider the group that has the codes 0 and 0. Now, in this example, using the contrast coding scheme that I set up a little bit earlier, there is no group that has values 0 and 0 for the two coded variables. Because of that, what that 0, 0 represents is an absence of information about which group a particular participant or a particular student is in. So if I said, hey, here's a student, she has the codes 0, 0, you would think about it for a second and then scratch your head and say, wait a sec, I don't know if this student in particular is in the failure group or the no feedback group or the success feedback group. Relatedly, what this is telling us is that in the absence of any information about which group you're in, we're imagining just the overall sample or the overall average of all groups. So what do we do here? We take that value, those values of 0, 0, and we plug them into our regression equation. Here's our basic regression equation here. The predicted value for a given person is equal to a constant b sub 0 plus a regression coefficient times our first code variable plus a regression coefficient times our second code variable. Again, we plug in 0, 0 for x sub 1 and x sub 2. That, of course, removes those two terms, and we're left with the predicted value for any person is going to be equal to b sub 0. Now we know the predicted value for any person, if we don't know anything about which group that they're in, is the overall mean. Or put a slightly different way, if I asked you about a given student, I said, what do you predict this student's level of persistence will be? How many tasks will she complete before giving up? But I'm not going to tell you whether she's being given success feedback or no feedback or failure feedback. Your best guess would be to ask me, well, what's the average across the whole sample, across all groups? And I might say, well, the average is 5 tasks or whatever it happens to be. And then you'd say, aha, that's my prediction. So again, we're plugging in 0, 0 for x sub 1 and x sub 2. We're solving, and we're using our understanding that that 0, 0 code corresponds to the overall mean across the sample, or the grand average of all students' scores. So again, just to repeat myself a little bit, b sub 0 is the prediction that the model makes when group membership is not known. Equivalently, it's the grand mean for across all participants regardless of group. You can use the following formula if you want. Pardon me. You can use the following formula if you want, which is to say it's the average of the averages of the failure group, the no feedback group, and the success group, if those group sizes are equal. And in this case they are. There are 8 students in each group. So we could say, if we want to very quickly compute the grand mean, we take the mean for the failure group, the mean for the no feedback group, and the mean for the success group, add them up, divide by 3. That's our overall mean, or our grand mean, because those group sizes are equal, and that's going to be equal to b sub 0 in this coding scheme. Okay, so now we move on and we solve for the group that has the code -2 and 0, and that's a group that actually exists in our coding scheme. That happens to be the failure group. So we take our regression equation, we substitute in those values for x sub 1 and x sub 2, we do a little solving, and we continue to solve by taking advantage of 2 pieces of information. If we know what group a person is in, then we know that the model's best prediction for that person's individual score is the average for that group. So if I don't know what group a particular student is in, my best prediction for his or her performance will be the overall average. But if I know what group that particular student is in, my best prediction for his or her score will be the average for that group. So I show you a student and I say, what's your prediction for how many tasks this student will complete? By the way, she's in the success feedback group. You would think about it for a second and you'd say, what's the average for just that group? And I'd say, well, it's 7 or whatever it happens to be. And you'd say, haha, that's my prediction for this particular person. So that's one piece of information we take advantage of. The other is that we already have solved for b sub 0. So we substitute in, you can see here, the average for the failure group for on the left side of the equation, and for b sub 0 we substitute in that formula of the average of all 3 averages for all 3 groups. And you can see I've done that right there, and you'll see why in just a second. So I'm going to take that same formula from the previous slide. I'm just going to continue to solve for b sub 1, just moving a few terms around. And you can see here I'm going to express the average of the failure group as 3 over 3 times the average of the failure group, because that'll allow me to do a little bit of subtraction. In just a second, I'm going to kind of break up that fraction there to make it a little bit more obvious what I'm doing. Okay, so there's that same formula from the previous slide. We can do a little subtraction there. move the 1/3 fraction outside of a bracket, and then put little parentheses around the term for the average of the no feedback group and the average of the success group. And then I'm going to get rid of that 2 on the left side of the equation by dividing everything by 2, or multiplying everything by 1/2. And the reason I did this is I wanted the final version of this equation to look a little bit like what it looks like right now. 1/3 of the difference between an average of 2 groups and the average of just 1 group. Now, why do I want it to look that way? Because I want to be able to interpret the regression coefficient b sub 1 as 1/3 of the difference between the average of the no feedback and the success feedback groups and the failure feedback group. So just like it is there. What's the average of those 2 groups minus the average of the failure group, and 1/3 of the resulting difference. So there's that same formula again, and if you just take a look at it, look at the portion that's within those brackets, it kind of makes sense. That's the contrast or the comparison that we wanted. We wanted to take the failure group and compare it to the average of the no feedback and the success group, and expressing the formula that way makes it pretty obvious that we got kind of what we wanted to get from that set of contrast codes for our first or I should say the contrast codes for our first contrast code variable x sub 1. Now you might be wondering, okay, but what about this 1/3 fraction that's outside of the bracket? What's that about, or what does that mean? Well, the textbook that we use for our class, Andy Field's Discovering Statistics with SPSS, doesn't really make this clear. Other stats books that I have sometimes refer to this term, this fraction, as a scaling factor. And what it kind of refers to or indicates is the number of groups that are part of this contrast. So our contrast here involves 3 groups: the no feedback group, the success feedback group, the failure group. And this 1/3, you can think about it again as a scaling or an adjustment for the presence of those 3 groups. So if you want to see how this works, you could go back to that table for the regression coefficients, and then you could also just produce some descriptive statistics for the different groups. So here I've just used the descriptive module in SPSS to give me the mean and standard deviation for each of my groups. And if I plug in the values for the means of the different groups into that formula and then just do the math, I end up with a value that's equal to the unstandardized regression coefficient for that first contrast, so 0.35. There's a slight rounding error there, but that really doesn't matter for our analysis right now. Now let's continue a little bit, and we'll talk about the group that is coded 1, 1. Again, we take our basic, I should say that's the success group in our coding scheme. If we take our basic equation, we substitute in those values, we know that the prediction for folks in the success group is going to be the average for that group. We've already solved for b sub 0, we've already solved for b sub 1. What we'd like to do now is solve for b sub 2, actually a whole bunch of algebra later that for the moment I'm going to skip. We end up with an equation that looks like this. And the equation suggests to us that b sub 2 is 1/2 the difference between the average for the success group and the average for the no feedback group. And if you look back to the coding scheme, that part there in between the parentheses makes sense. That's the comparison we wanted, and that fraction outside of the parentheses is again this kind of scaling term that we saw in the previous regression coefficient b sub 1. It's a fraction that kind of hints at or indicates the number of groups involved in that comparison or that contrast. But let's say you really don't like those fractions. You find them a little bit confusing. You don't want to have to bother to do the algebra or remember them when you're interpreting regression coefficients. What could you do? Well, if you don't like these fractional scaling factors, just use them to revise the original contrast codes. That is, take those original contrast codes and divide each contrast coefficient by the number of groups in the contrast. So formerly, our codes for x sub 1, sort of going down the rows in column for x sub 1, were -2, 1, 1. What if instead, because there are 3 groups in that contrast or that comparison, we now divide by 3 and we get codes for -2/3, +1/3, +1/3. Likewise, if we go down the column, or go down the rows in the column for x sub 2, originally our codes were 0, -1, and 1, but there are 2 groups in that contrast or that comparison. So let's just divide everything by 2. Obviously 0 is still 0. Our next code is -1/2 and then +1/2. Again, you might notice, if you are sort of really thinking about the fractions here, that what we're trying to do here is make each contrast equal to a difference of 1 unit. So the difference between -2/3 and +1/3 is 1 unit or 1 step. And equivalently or equally, the difference between -1/2 and +1/2 is 1 step. So if you just think about it for a second, you probably have the intuition that, aha, this allows us to get rid of those fussy little fractions. Now, SPSS won't allow you, at least I don't think it'll allow you, to enter fractions into cells. So what you do instead is enter decimal fractions. Just do the math and enter the values, because these are repeating values in the case of -2/3 and +1/3. Obviously they're repeating, they go on forever. I've just gone out to, I think it's 4 decimal places there and rounded. That's going to be good enough for me. The codes for -1/2 and +1/2 are, of course, fixed at their values, so that's pretty easy to do. Now if we take these codes and plug them in and do the algebra again, well, it's actually not that hard. For b sub 0 works out the same, because again we're talking about all groups, or the what we get when we solve for 0 and 0. So that's exactly the same as it was before. Our failure group now has the code -2/3 and 0. And so we have to substitute in -2/3 and 0 and start to do some algebra. Do a little bit more algebra. Rearrange some terms and do some more algebra. A little bit more. Almost there. And there we go. So we basically have b sub 1 equal to the average of the no feedback in the success group minus the average for just the failure group. So again, difference between the average of the no feedback and success feedback groups and the failure feedback group. Notice the difference here is we got rid of that 1/3 fractional scaling factor. So if you run a regression, except this time using those fractional values for our contrast codes instead of the original integer values we use. So you use the -2/3, +1/3, -1/2, +1/2, etc., etc. If you use those values and you run a regression, the overall model is the same. So the model summary and the ANOVA table will look exactly the same. The table for the regression coefficients will look a little bit different, because those values for the unstandardized coefficients, b sub 0, b sub 1, b sub 2, they're going to be a little bit different. Actually, b sub 0 will not. B sub 0 will be the same, but b sub 1 and b sub 2 will be different. And if you again just get your descriptive statistics, and if you plug in the values for those means and solve, you'll see that b sub 1 does in fact equal the average of the no feedback and success group minus the average of just the failure group. And again, there's a very slight rounding error, but that's not that big a deal. The important thing to notice here is, as I mentioned previously, we got rid of that somewhat tricky 1/3 fractional scaling factor. So it makes that value of 1.06 2 or 0.65 a little bit easier to interpret. So here's our original coding that's using the integer values for our contrast codes, the -2, +1, etc., etc. And here's our revised contrast coding. So you see that it's slightly different, specifically the values for B sub 1 and B sub 2, their unstandardized regression coefficients are a little bit different. Note that the test statistic, the t statistic, for instance, for contrast 1, and the associated significance level for that test statistic, they don't change. And you might be kind of wondering why that is. It is not immediately obvious, or it might not be immediately obvious, but what's happening is both the unstandardized regression coefficient and its standard error are changing or scaling by the same amount. So depending on our coding, we're going to kind of divide out or multiply out the value for the unstandardized regression coefficient and its standard error by the same amount. So it's kind of a draw or a non-effect. And if you think about what is a t-test is an observed value minus a predicted value under the null hypothesis, which is usually 0, divided by the standard error for that observation. So here that t value of 2.326 is equal to 0.354 minus 0 divided by 0.152. It's also equal to 1.062 minus 0 divided by 0.457. It gives you the same value for a t-statistic, and that value, 2.326, has the same has just one probability under a null distribution for the t-test statistic. So it's the same, which is kind of cool. The important point to notice here, or to note here, is that either way, whether you use the original integer coding or the revised sort of fractional coding, you can interpret the significance level the same way. What is different is how relatively easy it is to interpret the unstandardized regression coefficient. Okay, hopefully that makes sense. Let's move on and let's consider our last group. That's the success group. That's the group that has the code -1/3 and +1/3. So we're going to go ahead, get our equation, substitute in, start doing some algebra, do a little bit more where we take advantage of the fact that we know that the prediction made for people in the success group is going to be equal to the average for the success group. So here's that formula, rearranged slightly. We already know what b sub 0 and b sub 1 are, so we're going to throw those values into our equation. Do a little bit of algebra here. Do a little bit more. A little bit more. A little bit more. See, I told you there was a lot of algebra in this step. And so our success group has a formula that looks like this, and then we just divide by 3 and we get this formula here, which is great because we want b sub 0 to be the difference between the average for the no success group and the average for the no feedback group and the average for the success feedback group. Once again, if we look at those regression coefficients when we use our revised sort of fractional contrast codes, we look at those same descriptive statistics and we just plug in the values, we'll see that the value that we get, 0.063, that's the value for the average of the success group minus the average of the no feedback group, and it's equal to, allowing for some rounding, the unstandardized regression coefficient for that second contrast. It's a little bit easier to interpret then because we don't have to remember that, oh, there was that fraction of 1/2, so we have to multiply by 2. A few important points. contrast coding, however you do it, whether it's using integers or fractions, helps us focus on comparisons or contrasts, and usually they're ones that we want, ones that are related to hypotheses we're trying to test. Interpreting coefficients can be a little bit tricky. If we use whole integers for codes like -2s and 0s and 1s, then those regression coefficients are going to be scaled by the number of groups in our comparison. If we use fractional codes like -2/3 and 0 1/2, the algebra is harder, but the interpretation is a little bit easier. And I should note, you don't actually have to do the algebra every single time you do it. You can just create, if you want, a table of integer codes and then do the division like I did before, dividing by the number of groups in each contrast, and just trust that the algebra will work out. The reason I did it in the previous slides was just to kind of prove the point to you. But you wouldn't have to go through all of that algebra every single time. You could just create a set of codes using integers, -2s, 0s, 1s, whatever, and then just divide by the appropriate number of groups, 2 or 3 or however many groups are in a particular contrast, and you get some fractions that would work out just fine. It's also important to notice that the significance tests for those regression coefficients, whether they're based on whole integer coefficients, or whole integer codes or fractional codes, they work out the same. So in a way, if all you care about is whether p is less than 0.05, then you don't need to worry about fractions. I would argue that you probably do, or you should care a little bit about how different the groups are, and not just is that difference statistically significant. So I'd encourage you to at least think about this when you do these types of analyses for real. So all the preceding stuff has been about contrast coding, and if you've read the text or if you've been in class, which hopefully you have, you might be thinking, well, what about dummy coding? Isn't that easier than contrast coding? They're only 0s and 1s. There are no fractions. Isn't that easier to do? Can't we just do dummy coding? Yeah, you can, and we will in the next few slides, although I'll make the little point here that decisions about the analyses you do should be based on your hypotheses, not on how easy or how hard the analyses are. So you probably shouldn't choose to do dummy coding just because it's the easiest thing. You might choose to do it because it fits your hypotheses. So let's imagine that we do have some hypotheses that fit or are appropriate for dummy coding. Well, it'd be pretty easy to imagine what these would look like. You might say, well, negative feedback is worse than no feedback. So being punished by being told that you're a failure makes you feel worse than being told nothing at all. No feedback is a reasonable comparison group or kind of baseline group for our first contrast or comparison. Might have another hypothesis that positive feedback is better than no feedback. So being told that you're succeeding makes you feel better or makes you persist longer than being given no feedback at all. Again, the no feedback group serves as a comparison point or a baseline against which to compare or to make this second comparison or second contrast. So that's, you could imagine would work pretty well for dummy coding. It's also worth noting, like before, these comparisons, these hypotheses are directional in nature, so that's kind of useful. Assuming that we have a good theoretical or empirical reason to make directional predictions, we might choose to, just because they aid us in terms of statistical power and in terms of interpretation later on. But in any case, you make some dummy codes, they look a little something like this, probably, where the group that is no feedback gets 0, 0, and the group that is failure gets 1, 0, and the group that's success gets 0, 1. Now, the important thing to note here is that the group that gets the 0, 0 becomes the reference or baseline group for the other contrasts. In this case, it makes sense, I think, based on our hypotheses, to give the no feedback group the 0, 0 code. And to be clear, the failure group could be given 0, 1, and the success group could be given 1, 0. That's sort of arbitrary. The important thing is whatever group is the baseline or reference or comparison point, they're the group that has to get 0, 0. Also, it's worth noting that these comparisons are going to be non-orthogonal. Dummy coding comparisons or dummy coding contrasts are always non-orthogonal. That just happens to be the case here, and I'll talk a little bit later on about whether or not you should be concerned about that. So here's my SPSS data set. I've just added 2 more columns. These correspond to my dummy coding variables. You can see them right there, pretty straightforward, especially after all that messing around with fractions. I'm going to do the same thing I did before. I'm going to substitute in those values into my regression equation. So now, or this time around, I'm going to start with the code 0, 0. Previously, 0, 0 didn't correspond to any group, so rather it corresponded to the overall sample. Here, in dummy coding, 0, 0 corresponds to a specific group, the no feedback group. So when I substitute in 0, 0, I'm not looking at a prediction for the overall group, I'm looking at a prediction for those folks in the no feedback group, because they're my baseline or my reference. So I know that the predicted level of perseverance or task persistence for people in the no feedback group is going to be equal to b sub 0, and I know that that's equal to the average for the no feedback group. So what's this mean? Well, b sub 0 is going to be the prediction for the no feedback group, or equivalently the mean for the no feedback group. Moving on, I get the group that's coded 1, 0. That happens to be my failure group. I'm going to substitute in those values into the regression equation and start solving. I already know what b sub 0 is, and now that makes it pretty easy to solve for b sub 1. B sub 1 is just the difference between the average for the failure group and the average for the no feedback group. So just to summarize, here is our formula we've solved for b sub 1, and b sub 1 is again the difference or the contrast or the comparison between the failure group and the no feedback group, or the difference between the means for these two groups. Note here the fact that the b sub 1 is the average for the failure group minus the no feedback group rather than the average of the no feedback group minus the failure group is not important to us. It just worked out that way given the way we coded this group. We gave it 1, 0 and the algebra just worked out the way it did. That's not important, because what we want to be able to do is interpret the magnitude of that difference, regardless of whether it's in the positive or negative direction. Don't get confused about that with regards to the directionality of our prediction. Are we predicting a difference that's positive or negative? That really that's just something we make ahead of time, and we use that to either adjust or not adjust the p-value for our significance test. So if you're not too confused by that last little bit of commentary, let's move on. Let's talk about the success group. That's the group that got the code 0, 1. So once again, we're going to take our basic regression equation. We're going to substitute in those values. We're going to solve. Keep solving. There we go. We've got b sub 2 is equal to the average of the success group minus the average of the no feedback group. Isn't this algebra so much easier in dummy coding? There are just no fractions to screw around with. It's all just so simple to do. To summarize, b sub 2 is the difference or the contrast, the comparison between the success group and the no feedback group. This time round, the formula works out kind of in the direction we want, which is we'd like to see a difference between the average of the success group and minus the average of the no feedback group, because we expect that the folks in the success group will persist longer than those in the no feedback group. But again, that doesn't really matter. The direction doesn't really matter to our interpretation of the results. We're just interested in the absolute magnitude of that difference. Okay, so if you run the regression again, this time, rather than using either set of contrast codes, you instead use your new set of dummy coded variables. The first thing you notice is that the model summary and the ANOVA table look exactly the same as the previous analyses. That should be no great surprise because we're taking the same amount of variance, we're just carving it up in different ways. If you look at the table for the regression coefficients, you might notice first that neither contrast is significant. Neither the contrast for the first one nor the second one. You might also notice that if you just look at your descriptive statistics and then plug in values for means, that B sub 1 does in fact equal the difference between the amount of persistence in the failure group and the amount of persistence in the mean for the no feedback group, and B sub 2 does in fact equal the difference between the mean for the success group and the mean for the no feedback group. And as I mentioned earlier, when we do dummy codes, we don't end up with any sort of fractional scaling factors, so that's kind of cool. Or at least it's relatively easy. It's easier to do just a quick interpretation of what B sub 1, what B sub 2 actually mean. Now the fact that those contrasts, neither of those contrasts is significant, probably won't come as a surprise to you, again, if you'd made the graphs ahead of time, because you can see that first contrast is comparing no feedback and failure group, and in that case the error bars for those two groups overlap quite a lot, and they each overlap with the mean of the other group, and likewise the error bars, in the second contrast, no feedback group compared to success, the error bars once again overlap a lot and each overlaps the mean of the other group. So you might guess ahead of time, like, gosh, neither of those contrasts is likely to be significant. So at this point, you might have this lingering thought in your mind, lingering question, what about orthogonality? Contrast codes can be orthogonal. It depends on how you do them. And if you want to check their orthogonality, you just take the little table or matrix you've created and sum the products across the columns. And if that sum equals to 0, and if you have equal group sizes, you don't have a problem, or rather your codes are orthogonal. So if you were to multiply across the columns and then take that new column of products and add them up to 0, that's your kind of quick rule of thumb way of checking the orthogonality of your codes if you have equal group sizes. In comparison, dummy codes are just never orthogonal because they always involve repeatedly comparing groups to one baseline or reference group. And you may be thinking, should I worry about which to choose? Is there some relationship between my choice of coding schemes, orthogonal or non-orthogonal, and the family-wise error rate that I might have to worry about across a group of comparisons? Now, we've talked about orthogonality and non-orthogonality a little bit in class. We've talked about family-wise error rate a lot in class. Maybe some of you are sick of hearing about it. So here's a summary of my advice. I'd say the first and probably the most important thing just in general in statistical analyses is to have good hypotheses. Try and have hypotheses that are specific, that are directional if it's appropriate. And again, that depends on what the theories in your field and what the past literature in your field allow you to say about what you think is likely to happen. And importantly, have a limited number of hypotheses unless you're really doing exploratory research and you're willing to be very honest about the fact that you're just fishing around for possible findings. Be specific, be directional if limited, and if appropriate, and be limited. Then choose the codes that allow you to test your hypotheses. Again, limited numbers of tests as possible, or as small a number of tests as you can possibly get away with. The greater the number of tests you do, orthogonal or not, the greater the family-wise error rate you're going to have. The greater the type 1 error rate will creep up across all of the tests that constitute that family. So the point I'm making here is don't maybe worry too much about orthogonal versus non-orthogonal. Think about, what are my hypotheses? How can I test them efficiently and clearly? That said, if it's possible to make a preference, I tend to prefer orthogonal contrasts for a couple of reasons. The first reason is orthogonal contrasts tend to be smaller in number than non-orthogonal contrasts. That means if you have a particular predictor variable or factor that has, let's say, 5 levels or 4 levels or however many levels it has, however many groups there are in that predictor variable, it's almost always the case that the number of orthogonal contrasts you can make with those groups is going to be smaller than the number of non-orthogonal contrasts. So some textbooks will kind of point out or argue that if you really get into doing non-orthogonal contrasts, just like lots and lots of dummy coding, it's very easy to, without meaning to, just test a lot of comparisons. And that tends to, of course, increase the family size and increases the family-wise error rate. The other thing, so in that sense, orthogonal contrasts have a slight edge or are slightly preferable. The other thing that's nice about them is the interpretation of them tends to be a little bit cleaner, and I'm kind of putting the quotes around that because it's a bit of a vague descriptor, but here's what I'm trying to get at. Here are the groups that we've been looking at, and let's consider some orthogonal contrasts, the ones that we did. Regardless of whether we were doing integers or fractions, our first orthogonal contrast compared the failure group, of course, to the no feedback and success group, and our second orthogonal contrast compared the no feedback group to the success group. So if we put these both together, kind of try and visualize them at the same time, hopefully you kind of get the sense that the size of the effect in one contrast has no relationship, that is, it is orthogonal to the size of the effect in the other. Whether or not the failure group differs from the average of the feedback in the success group has basically nothing to do with whether or not the feedback and the success group differ from each other. They are unrelated, they are uncorrelated, they are orthogonal. It's like, those three columns in our bar graph are pieces of a sheet cake, and we're sort of slicing off one chunk. That's our failure group. We set it off to the side, somebody eats it, now we're left with less cake, and we slice out the remaining into 2 pieces, if we want to use the whole cake metaphor thing. Now compare that to how this would work if we had our 3 groups again and we did the dummy coding approach to produce non-orthogonal contrasts. Here, our first non-orthogonal contrast compares the no feedback group and the failure group. And then our second non-orthogonal contrast compares the no feedback group to the success group. So once again, if we try and visualize them together at the same time, you hopefully get a little bit of a sense that the effect size of one contrast, say the first one, is related to, at least a little bit, is correlated with, is not orthogonal to the effect size for the other contrast. So the dummy coding means that each feedback group, success or failure, is compared to our no feedback group. It's our baseline or our reference point. And that means that the extent to which the no feedback group is higher or lower than the failure group is related to the extent to which the no feedback group is lower or higher than the success group. The one comparison has some sort of bearing or some sort of connection to another one. At an extreme, you could do lots of non-orthogonal contrasts, searching to find one group that differs from the baseline, searching for another, does this group differ from the reference group? Oh, what about this group? What about this group? What about this group? And if you did, all of those comparisons or all of those contrasts would be at least slightly related to one another, which makes them seem at a kind of an intuitive level more closely bound together as a family with respect to that baseline group than a similar number of orthogonal contrasts. Now, to be clear, some of this goes to how you define a family. And if you had 4 tests that were orthogonal contrasts and 4 tests that were non-orthogonal, some people, even me, would argue that the family-wise error rate for both of those sets is about the same. However, some people, and sometimes I'm one of them, would say but it's kind of worse if they're non-orthogonal because they're more closely bound. You're more likely to be essentially asking and answering the same question repeatedly, sort of in the hopes of finding a significant difference or a significant effect that you can report. And to make this even worse, you could imagine doing lots and lots of these comparisons, especially if they're non-orthogonal comparisons, and then only selectively reporting the one significant finding you had, putting all of the rest of them in your figurative or literal file drawer, or I guess nowadays computer hard drive. This could be really misleading to your readers and could tend to distort the research literature. As I've talked about in my classes, and as you have hopefully noticed, regardless of whether or not you've been paying much attention to me, this is a big, it is hard to overstate how big an issue this is for psychology and for other sciences as well. The idea that some of our most apparently well-established effects are not robust has a lot to do, maybe not entirely, but a lot to do with the fact that people don't report all the tests they do. They only report the ones that are quote-unquote statistically significant. And that's a problem. Important points to focus on, or to make here. First, just focusing on specific limited numbers of tests. This makes the whole issue of orthogonality less serious. Like, are my tests orthogonal? Are they non-orthogonal? I don't know. I'm confused about what orthogonality even means. Look, at the end of the day, if you're doing a small number of focal, theory-driven prediction testing tests, then you're probably in pretty good shape. And also, and this is important for all of us, especially as we go forward as a science, let's try and report clearly and honestly what we are doing, how many tests we are running, how many are significant, how many are not. Because failing to report the results of tests, especially failing to report null findings, regardless of orthogonality of those tests, is wrong, or at least it's misleading. All right, well, that was a bit of sermonizing on my part, and I don't know, some of you who are in my classes might find this stuff interesting or even inspiring. Some of you may find it kind of boring or irritating, but the replication crisis in psychology is a big deal, I think. But to bring it back to our supplemental lecture on planned contrast, we talked about contrast coding, we talked about dummy coding. You might be thinking, well, what about polynomial coding? You mentioned polynomial coding in your lectures. It's covered a little bit in the book. In this case here, when we look at this data, it seems like there's a natural trend across levels of our predictor variable, across, that is, our different groups. The failure group is a little bit less than the no feedback group. The no feedback group is a little bit less than the success group. Those differences seem roughly equivalent, thus suggesting kind of a straight line linear trend across all three. Again, I'm going to throw in one of my little notes here. You should probably have some sort of a theory about a trend rather than just, hey, I looked at the data, it kind of looks linear, or hey, I looked at the data, it looks quadratic. But let's assume you had some reason to predict a trend here, a linear trend. Let's say you had some hypotheses. One is that behavior increases as teacher feedback becomes more positive. So let's imagine that failure feedback or negative feedback is as bad as it can get. No feedback is relatively speaking more positive because at least you're not being punished. And then positive feedback is even better than that because now you're getting feedback and it's good feedback. So you could imagine hypothesizing kind of a rectilinear increase in how much people or students would want to persist as the feedback they're getting from the teacher becomes relatively more positive. That could be one hypothesis that would be consistent with a linear trend. You could also make another hypothesis that any attention is more reinforcing than no attention. This is something that maybe parents of small children can appreciate, that sometimes it really seems like you could be praising a child or insulting a child, not insulting, but let's say yelling at a child, and that seems to get their attention a lot more than giving them no feedback at all. So you might make the prediction that student persistence will be highest in the failure and success groups relative to the no feedback group. That prediction would be more consistent with a quadratic trend, not a linear trend. So how would you represent these in terms of codes? Well, it's actually not very hard. You could set up a series of codes that look like this. The first set of codes, that is x sub 1, examines the linear trend because of course we're stepping up by units of 1. 1 to 0, 0 to 1. Those are each equal steps upwards, of course, and that's the prediction we're making. The second set of codes are our quadratic trend, so where we're predicting higher performance in the failure and success groups, equivalently higher performance, and less in the no feedback group. Notice that these are just contrast codes. They're not really any different than the other contrast codes we talked about earlier, except that they kind of have an implied trend that goes across them. Notice also that these codes, at least the way I've set them up, are orthogonal to each other. So for instance, if you multiplied across the columns, -1 times 1 is -1, 0 times -2 is 0, 1 times 1 is 1, then you add up -1, 0, and 1, you get a total of 0. That's your quick and dirty way. It's not really dirty, it's a quick way of checking the orthogonality of these codes. These are orthogonal polynomial codes. When we run this analysis in regression, we need to enter both sets of codes to fully represent the levels of the predictor variable. So let's imagine you really only cared about that first linear trend. You didn't really make that second prediction or the second hypothesis about the quadratic trend. Your coding, -1, 0, and 1, is now slightly incorrect or incomplete. You need both sets to fully represent all levels of the data, such that each group has a kind of a specific code. So and with only 3 levels of our predictor variable, that is, there's a failure group, a no feedback group, and a success group, there are really only 2 possible polynomial trends we can test. One is the linear trend, the other is the quadratic trend. So go ahead and test them both. One last point is we could make this quadratic trend in a couple different ways. So for instance, we could make the prediction that the failure group and the no feedback group would be equivalently would have equivalently lower performances relative to the success group. That would imply kind of a line with a bend in it or a kink in it as well. The trick here is that now that set of contrast codes is non-orthogonal. Previously I'd set them up to be orthogonal, now they're non-orthogonal. So -1 times -1 is 1, 0 times -1 is 0, 1 times 2 is 2, 1 plus 0 plus 2 is 3. So that's our quick way of checking that these contrast codes now, these polynomial contrast codes, are now non-orthogonal to each other. Now, that's not necessarily a bad thing. It doesn't mean we can't do them. It just means that we would have to, again, entertain the possibility that we're kind of repeatedly testing portions of the same variance, slicing and returning bits of the same piece of cake, if you want to persist with that metaphor. One more point, we could also create fractional versions of these codes just as we did with regular contrast codes, dividing to create fractions if we wanted to. You don't see this as much, or at least I don't tend to do this as much personally. That's because interpreting polynomial contrast kind of has more to do with the overall trend than the magnitude of specific steps. So if you're testing a linear trend, you're not so much concerned about, well, what's the difference between level 1 and level 2, and what's the difference between level 2 and level 3. You're more like, is it generally the case that as we go across levels, the outcome variable rises or the outcome variable falls? So the exact magnitude of the regression coefficient is less interesting, so often we don't bother to create these fractional codes. But you could. I mean, there's no reason why you couldn't. You just apply the same rule as you did before. For the code x sub 1, there are 2 groups involved in that contrast, in a sense, because one group gets 0, so we're just going to divide divide by 2, and now we're going to do our next set of codes. We've got 3 groups for x sub 2, we've got 3 groups involved, so we're going to divide by 3. That's pretty simple that way. So here in the very last 2 columns of my SPSS dataset are my polynomial contrast codes for my linear and quadratic term. So if you enter these polynomial contrast codes into the regression module of SPSS and basically run the regression again, you would notice first of all that the model summary and the ANOVA table look exactly the same as all the previous iterations of this analysis that we've done. That hasn't changed at all. What has changed are the values for the regression coefficients. And if you look at the table here and especially look at the significance levels, you would see that the linear trend is significant, which makes sense if you take a look at the graph. It seems pretty obvious that that there's a linear increase in the mean level of task completion across these three groups. I haven't probably talked about this as much as I should have in class, but trend analysis like this, when it's appropriate, can be really handy because you can accomplish with one test what might have taken you 2 or 3 or 4 tests using pairwise comparisons. So trend analysis we sometimes like because it's efficient. Smaller numbers of tests, smaller families of tests, less worry about family-wise type 1 error. Okay, let's quickly review what we've learned today. Well, we know that there are different kinds of coding schemes. Hopefully you know that by now. There's dummy coding. That's really the easiest to make and interpret. There's contrast coding, which is more complicated because it can be integers or fractions. They can be orthogonal or non-orthogonal. And then there's polynomial contrast coding, which is really just contrast coding, but it works when there's a natural order to the levels of the predictor variable. This is especially sensible if you have different doses or different intensities of a stimulus. Here we're kind of making the argument, in my example at least, that there's some sort of linear relationship between negative feedback, no feedback, and positive feedback. That seems sensible to me, but probably it's not the best example of a situation in which you would reasonably conclude a natural order in the levels of the predictor variable. Understanding these different schemes I think is really useful. It allows you to get comparisons that you want. Do a limited number of tests that let you compare the groups or the groups of groups that you really care about, or compare trends across groups in a way that's efficient to test your hypotheses without doing a lot of extra testing, which would necessarily increase family-wise error rate. Understanding these coding schemes is really useful because it also allows you to interpret regression coefficients, because you can see them as differences or sometimes fractional differences between groups or groups of groups, and that's important. So you're not just focusing on is p less than 0.05, you're paying attention to that, but you're also thinking, okay, well, if p is less than 0.05, how big is the difference between group 1 and group 2? How many more tests does a child persist on if she's given success feedback, positive feedback, as compared to no feedback? Is it just a couple extra tests, or maybe she really keeps going for a long time? We often want to know more than just a significance level or the results of a hypothesis test. We want to know the practical size of an effect, or even the calculated effect size, which I didn't really talk about much here. Gosh, speaking of persistence, if you persisted at this point all the way through this lecture, good for you. It took me a long time to write this lecture. It took me a long time to record it. Gosh, I was making so many mistakes. I had to keep on stopping and restarting. I'm happy I'm done. And hopefully you're happy you're done. And hopefully you've learned a little bit along the way. That's really the goal of all of this. So, pour yourself a cup of tea, pour yourself a cup of coffee, let all these ideas sink in a little bit. And if you have questions, let me know. And as I always say, gosh, thank you for your attention. I do appreciate it. I know this is tricky stuff. It can sometimes be frustrating. So thanks for paying attention. Bye-bye.